In recent years, Japan has a shortage of highly skilled doctors. In particular, this problem has led to a significant decrease in providing superior training of surgical procedures to medical students. Mentoring students in a proper environment is replaced with lectures and workshops. There is a need to provide an efficient surgical training to our future doctors. Currently, medical students attend clinical practice to gain initial exposure to technical procedure and processes in the surgical environment. A highly skilled surgeon is assigned to mentor on average 5 medical students. Although the basic procedure and simple devices are sufficient during early training, advanced training requires extensive mentoring in full-scale surgical facilities. Presently, minimally invasive surgery is rapidly progressing. However, advanced skill development is required, such as the precise operation of forceps under a narrow field of view. In a typical laparoscopic cross-ischemic operation, bleeding and organ damage occur, and in the small numbers, even death. Hence, technical training is vital. In addition, the size and arrangement of organs vary among patients. For example, the variation of cytic duct. Extensive training is required to fully understand the anatomy and surgical process involved in such operation. Simulator training system is recently utilized in laparoscopic surgical training. For example, simulator training has been obligated in the United States because of its outstanding reviews. Although these devices are deemed important for training, in Japan it is difficult to import and maintain a large number of these expensive foreign devices. In such training system, a number of medical students take turns in using the simulator. This is inefficient because students are forced to train in limited duration. Other than that, simulator must contribute to a lifelong education of our doctors. Thus, the simulator must be customized to suit regional disparities in medical technology. Therefore, we achieved a domestic low-cost device and developed a network laparoscopic training simulator that can provide efficient mentoring to a large number of medical students. In this simulator, the VR training environment reproduces a hand-on training method as if the doctors are beside the student and guiding their hands to perform the surgical processes. We set up the simulator at each particular location and link them via network. An instructor, highly skilled surgeon, can control one simulator and the other simulator will receive the same visual, and the student will also feel the tactile feedbacks. In effect, we can achieve a one-to-many training system in case where there is a student who have trouble with the training. A one-to-one training system can also be performed. Instructor can provide guidance that reproduces hand-on training, where instructor can guide the hand movement of the student. And by switching to a network training system, the training can be done to accommodate multiple students. With the application of this technology, we can set each role of the surgeon, camera assistant, and assistant in multiple locations. It is possible to perform real-time remote collaboration of minimally invasive surgical exercise. In addition, constructing a 3D model of CT scans for preoperative planning is becoming less difficult. Hands applications such as surgical planning and preoperative rehearsal between surgeons in remote location is also viable applications. To achieve the simulator, it is required an efficient tissue deformation model which can simulate the deformation with high reality and computationally fast and provide validity of operation. The deformation model is loaded on the adapted tetrahedral mesh model. We developed this model for multi-resolution modeling. A binary tree is generated by recursively bisecting the tetrahedron. The tetrahedron only produces 3 sub-tetrahedrons. Thus, the mesh quality is high and isotropic, providing the important feature of smooth resolution. We apply the model to the deformation simulation of online remesh method. We have achieved an adapted, co-rotated, embedded deformation model. Presently, we emphasize on computational efficiency and consideration of non-uniformity of the organs and tissues. The online remesh deformation simulation performs dynamic refinement when the deformation areas becomes larger. The simulation process among simulators must be shared and synchronized. We also discussed the synchronization process of the simulation. If the operation parameter at the same time may be shared among all simulators, the visual and haptic responses of each simulator should be same. However, there are delay of communication, jitter, packet loss, and other discrepancy in real scene because of various reasons. To different computer specification at each location, network condition, and so on. In our work, the value of the errors in deformation is constantly being evaluated. We solve the delay by only sending and receiving the necessary keyframe information of deformation from each simulator through efficient replacement using logical operations. In order to provide a high-quality clinical service, it is essential to build patient-specific 3D model of the organs. The fundamental step is the accurate and fast segmentation of the organ and tumors, which is also an important technique for clinical applications. Our proposed method had two main steps. The first step is the interactive segmentation of the liver and tumor from a 2D slice image selected by the user. We select the slice image with the largest liver area and set the C point for each object manually. The red and green are C point of the liver and tumor respectively. The blue are C point of the background. Then we use the Gaussian mixture model to enhance the liver and tumor region. After enhancement, the random walk-based method is used to segment the liver and tumor simultaneously. In the second step, we use the initial segmentation result to generate C points for each region automatically using morphological filter and a narrow band technique. Then the 3D liver and tumor can be automatically segmented by the random walk-based method. The advantage of our proposed method are 1. We can construct the 3D model of the liver and tumor from the patient's CT image by only 3 minutes. 2. We can construct model of multiple organs simultaneously. 3. The segmentation accuracy is more than 90%. Our proposed method will be an important and useful technique for computer-aided surgery and computer-aided diagnostics. To verify our research result, we conduct a collaborative simulation experiment connected to a network. The visual and haptic responses can be shared across all sites. For example, the position of the gallbladder was elevated at one site. The same content in one simulator location is shown in the other locations. In this case, the operation of the instructor controlling one simulator are displayed in other simulator, which show that one-to-many training is possible. By following the teaching of the instructor, users on the other sites were able to perform the operation. This shows that the same surgical environment can be reproduced across all surgical training simulators. Through this video, we are able to show the effectiveness of cooperative experiment between 3 simulators situated in Ritsumeikan University, Shiga University of Medical Science, and Higashiomi General Medical Center. In the future, we aim to spread the application of sophisticated devices into the school curriculum.